So you would gain a complete graphical understanding of what exactly the double integrals do in order to evaluate the given volume of the sphere. It is nothing but a stack up of plates of varying radius. But if you want to exploit the symmetry and integrate from 0 to r and double the resulting value of the integral, then also you will get the volume. When integrated along the y-axis between minus r to plus r goes to form the entire hemispherical volume. Now, in the previous discussion, we did look at the application of double integral to evaluate area. That was very straightforward because we were dealing with a simple circle. Now, let's extend the idea of double integrals to evaluate volumes. One thing I made it very clear, if you are just integrating the elemental area, and if you are using double integral, you would get your area. But along with the elemental area, if you use f of xy, which is equal to the third variable, since we are in the Cartesian space, if I say my third variable is z, and if you are multiplying z with elemental area, that is dx and dy, and then integrating, that is using double integral, then you will end up with the volume. So now let's look at how exactly it is done and what are the incidental observations. That's very important. So you would gain a complete graphical understanding of what exactly the double integrals do in order to evaluate the given volume of the sphere. So all observations and graphical understanding is very critical. So follow this discussion as earnestly as possible. So let's get started. Now, as we did previously, we will start with this single integral and then evaluate the volume, because that's what exactly we did. We used a single integral to evaluate the area of the circle. Now, how would you actually conceive the volume of the sphere? It is nothing but a stack up of plates of varying radius, and the symmetry that you need to appreciate here is that if you looked at the equatorial diameter, above and below you have the exact stack up of plates, and therefore even if you integrate the area of the plate multiplied by the thickness of the plate between minus r to plus r, also you will get. But if you want to exploit the symmetry and integrate from 0 to r and double the resulting value of the integral, then also you will get the volume. So how do you go about it? First, let's evaluate it by single integral. It's very simple. So the area of the plate from the diagram, it's quite easy to conceive by using Pythagoras theorem, knowing that the radius is r square minus y square will give me this radius from the Pythagoras theorem, because this is y, this is r. So this is the right angle, and r becomes the hypotenuse. So therefore you get the radius, and radius square multiplied by pi will give me the area of the plate, and that multiplied by the thickness of the plate will give you the elemental volume. So, and what could be the limits? Let's say that it is from minus r to r. Otherwise you can exploit the symmetry and you can say 0 to r and then double it. So this gives you the volume of the sphere. The point of observation here is that this integral is expressed in terms of only one variable. That means the limit that you are going to choose is with respect to only that particular variable, and therefore it is just one single integral that would give you the volume of the sphere, which is 4 by 3 pi r cube. Of course, it's quite easy to integrate because this is r square minus y square, and multiplied by pi dy, and then minus r to plus r, and r square, if you integrate, you will get r square y minus y cube by 3, and then if you put the limits, of course pi will come, minus r to plus r, if you put the upper limit, it turns out to be 2r cubed by 3, and if you put the lower limit, of course that also is going to be adding on to this, so that would become 4 pi r cubed by 3, which is the standard formula for volume of a sphere. Now this was just the +2 stuff. Now let's move on and understand how exactly this can be re-represented. That is, this integral can be re-represented using this double integral. Let's try and do that next. Now, I told you one thing very categorically in the preceding discussion, that if I am talking about the double integral, or a region, and if I say that I am using the elemental area, then this gives me only the area of that particular region. Okay, so whether you express this in terms of the polar coordinates, whether you express this in terms of the Cartesian coordinates, you are going to get your area. That's very clear. But if I am going to say that I am going to integrate f of x comma y dx dy, and assuming in the Cartesian space that this is my z, then this would give me volume. These ideas have to be absolutely clear to you. If you are using double integral, if you are just integrating the elemental area, you are going to get area. If you are integrating f of x comma y, which happens to be the z coordinate, okay, of a particular surface, we are going to talk about the spherical surface, then if you integrate z with respect to and multiply that by the elemental area and then integrate, then you will get volume, right? Depending on what you are integrating along with the elemental area, this is a must, along with the elemental area what you are integrating, that decides your output. So here, since we integrated only the elemental area, I get the area. If I integrate z along with the elemental area, so we will get the volume. And this z, if it is determined by the spherical surface, then you will get the volume of that spherical space. Now let's try and do that in earnest. Now, in order to develop or formulate the double integral, the first thing is I will have to consider the elemental area dx dy. The second thing I told you that I have to have z, which is derived from the relationship of the surface, because I am interested in the volume that is enveloped by a particular surface. Here the volume is being enveloped by the spherical surface, so therefore my z must be derived from the equation of the sphere. What is the equation of the sphere? It is x square plus y square plus z square is equal to r square. Because this equation is very easy to conceive and derive, because every point on the sphere is at an equal distance from the center, and if you apply the center distance formula, this result becomes very obvious. Now if I deduce the value of z from this turns out to be r square minus x square minus y square. So this requirement is also fulfilled. So now I am going to integrate this expression with respect to x and y in tandem, and that would mean that I am multiplying the elemental area by z and then carrying out the integration, which obviously gives me the volume. Now you can see here, as I compute my z, and then multiply that by dx and dy, I in fact end up getting an elemental volume. And as I integrate it along the x direction first, what happens, you can see the elemental volume that is formed, which is almost like a plate kind with a curved edge, and that plate is integrated along the y-axis. That means many such plates with increasing height, the curved plate with increasing height is integrated along y, and you can see that the hemispherical volume is formed. And when you double that volume, you can see that the entire sphere volume is got. And this is what the double integration process is all about. First you compute the elemental volume, then integrate along x, and you would see that a plate with curved edge is formed, and that plate, when integrated along the y-axis between minus r to plus r, goes to form the entire hemispherical volume. So I think this clarifies very, very categorically the entire process of double integration. So let's try and understand the limits. Now, the order of integration becomes very important. Here you can choose either to incept with x or y, but we have decided to start with the integration with respect to x. So my z is given by r square minus x square minus y square. Now let's say that first I want to integrate with respect to x and then with respect to y. Now, in order to integrate with respect to x, I need to fix the limits of x, right? Which is very, very obvious. Now, if I say I want to fix the limits of x, I need to look at this particular line. I know that this height is y and this radius is r, and therefore this becomes my limits of x. So what is that x? That x is obviously given by the Pythagoras theorem, that is r square minus y square, right? So therefore when I say minus, this is going to be this. If I say this as x dash, just to avoid confusion, minus x dash to plus x dash. So that becomes my limit. And you can see that when I actually carry out the integration with respect to x, what exactly I am getting? I am getting the area of a plate of a certain thickness with a curved edge, and you can see how exactly it is getting formed. And these are the limits minus x to plus x, which is r square minus y square. That is from minus root of r square minus y square to plus root of r square minus y square. And once that plate is formed, then I want the entire area of the hemisphere, and what would I do? I would integrate with respect to y. And if I carry out the integration with respect to y, what would be my limits? Would be from plus r to minus r. Because you can see that the plate is sweeping that entire space and then getting formed the hemisphere volume. And therefore what happens here? My limits are going to be minus r to plus r. And if I rewrite this with all the correct values, that is replacing x dash by its actual value, what I would get, minus r square minus y square, and here it's going to be r square minus y square, and of course this is r square minus x square plus y square dx dy. Now at the plus 2 level, you would have dealt with the square root functions, and you would have found it very, very difficult to integrate. There you would have made a substitution, right? Either x equal to a sine theta or y is equal to a cos theta, whatever, I mean, depending on the nature of the integral. But now here also we are going to do the exact same thing. In fact, looking at the nature or complexity of the integrand, what you can do is you can actually switch to polar coordinates. In fact, that's one of the techniques that's a part of the curriculum, that as we progress, you would learn how to switch from Cartesian to polar coordinates, which in fact significantly reduces your mathematical effort and makes life very, very easy. Now we have formulated our double integral. What we did, we computed z, and that was pertaining to the spherical surface, right? For a given xy, for that sphere, what is your z coordinate? And that is what we were interested in. And you can see how it is formed. the elemental volume when you multiply the elemental area dx dy by this z, which is corresponding to the spherical space. And then when I integrate it between minus, let me also say this x dash, and when I integrate it between minus x dash to plus x dash is this, because this can be computed from Pythagoras theorem, because that element is located at a height y and the radius of the sphere is r, and therefore x dash is this. So between minus x dash to plus x dash, you can see that the curved plate is formed. Okay, curved plate is formed of thickness dy, and you can see that when I integrate that curved plate, that is, that area is integrated, because that area is expressed obviously in terms of the x and y and r numbers, and that is integrated from minus r to plus r. Then you can see that sweeps the entire hemispherical volume, and you have the hemispherical volume formed. And as a consequence, what we do is we get the hemispherical volume because of this integral, and when I double this, I will get the volume of the sphere. As simple as that. Now, in the previous discussion, you clearly saw that how a double integral, when you integrated the elemental area, gave you area. Now that elemental area is multiplied by the z coordinate, and that z coordinate is obtained from the surface of our interest. If you put arbitrary z coordinate, it will give you arbitrary volume, but this is constrained to be part of the sphere, because where you are choosing your x and y, at the same point you are choosing your z, and therefore it gives you an elemental volume within the sphere, and that when integrated gave you a curved plate volume, and when that further integration was carried out with respect to y, you got the entire volume of the hemisphere. That's very, very important. So once again, please visualize how exactly the volume is getting formed, and then appreciate the limits that come about of that of the x, and also appreciate the limits that come about that of the y, and therefore now you understand this particular integral very well. You know how this expression got, you know why we started with this, because this gives you the elemental volume, and that volume is integrated with respect to the two variables that go to define that elemental volume, and those variables have the limits minus root of r square minus y square, that is the first limit of x, and the positive limit of x is the upper limit of x is root of r square minus y square, and that of the y are minus r and plus r. So that is that is the one situation which gives you a complete visualization of how exactly a double integral works in order to provide you the volume. You can apply it to any situation. All that you got to do is just the following. So as a take home, all that you want to do for a double integral to get the volume, z into dx dy. This z is defined as follows, because you want to find the volume of a specific surface, so therefore this should be the relationship. The limits of x here, let's say x dash, x double dash, and then limits of y, y dash, y double dash. I have just put it arbitrarily, so this gives you the volume. This gives you the volume. The only challenge would be, as the complexity increases, how do you fix these limits? Of course, we will have number of worked examples for you to visualize how exactly this is done. But this is the take home. If you take off z, what you are left with is just the area. If you plug in z, what you are left with is just the volume. So let's move on and look at more interesting discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.